we get 4 functions, compiled functions. If we do, let's do series.a of that, and let's also disassemble it. Disassemble that function. Let's make this bigger. Yeah. Very, very simple function. We're just, setting up a stack frame, moving our integer 1 into place, and then that's it. Easy, easy, easy. And that's our constant function 1. So the only thing is I need to fix that compile stuff. So let's do compile. Let's CLHS compile. Warnings P and failures P. So the conditions of type error warning and true otherwise. Alright, so what I'm going to do is just do this. Unless we're going to just say warning, warn. Let's do that. Let's delete this for now, and let's also do warn. Compilation of expression contains errors. Let's do that. So let's try this again. Good, we get 2 warnings. And we get our stuff back. Looks good. Critically, if we were to use CL store as an example, let's do hypergeometric. Let's do this. If I make this EXP series. Okay, so now I made something that allows me to specify in a serializable fashion the structure of a series. I can now use libraries like CL store to actually store our object. So let's store this to, I forgot, does this need a file name, I think? I'll do scratch foo.obj. So it stored it. Now if I restart my Lisp, let's QL quick load Hypergeometrica. So I just restarted my Lisp. Everything was cleared out. And in the package, Hypergeometrica. And if I QL quick load CL store, I do CL store restore scratch foo.obj, then I get back a serializable object. Again, this is something that was serialized and written to disk. And if I describe it, I get my lambdas, normal. But critically, if I do reify bin split series of, I think it's star that I can do. Nope. I need to do star star. If I reify it, then I can compile it. So this is a demonstration of the fact that I can store something to disk, later in a completely different Lisp session reload it, and then furthermore compile it on the fly. So the idea is when I want to compute pi, or compute any hypergeometric series, what I would do is compile or have a representation of the series or computation that we're going to reify. I could make my serializable, I think I'm repeating myself. I would make my serializable series, store it away on disk, distribute that series to all of my compute nodes. Then I'd have my compute nodes read in this file, load it, deserialize it, and then reify it to have compiled code on the nodes. So it's a way of sending compiled code to each of the nodes, or it's a way of sending code that can be compiled on demand to each of the nodes, which you can use to start a calculation. I think I'll finish up this this stream. I'll probably do about 9 more minutes by maybe doing one other thing. The last thing I think I'm going to do is demonstrate or show, let's see, what would be the next thing to do? The next thing I think I would start working on, maybe I'll move this to the next session next week or something, is the actual planning of the computation. So we're going to set up this big computation. We need to plan it. We need to plan it so we can break it and checkpoint it and so on. What we can do is figure out how much work we want each node to compute and then sort of make a queue. The way I imagine this working, so I'll spend the last 9 minutes not coding, but showing how I'm going to implement the work queue. So let me just go into the REPL. If I want to compute a series of 1,000,000 things, then probably there's going to be the work divided up into, let's say, 100 work units. So I have 100 units of work that each slave node is going to need to do. So I'm going to have to represent when these work units are done and so on. One way we might be able to do that is first we need to represent whether a computation is done or not. So we want to make a kind of work list of 100, element type, bit, and initial element 0. Whoops. I need to do this. So what this represents is a bit vector containing 100 notes. And so when something is done, let's say the 8th work unit is done. Let's say let work done be this. So work done, just to be clear, is initially that. But let's say the 8th one is done, and I can set up the bit of the work done of 8 to be 1. And let's return from that the work done. So we see that the 8th one is done. And the idea is that we maintain this expression right here until all of these are 1. When they're all 1, we can combine all the computations. We can either do all computation combination in one go, which is a possibility, but another smarter possibility might be to actually send the combination to a node, possibly. If we have 2 adjacent ones, let's say we do this, s bit 8 to 1, and whoops, let me go back up, and let's go down, and 9. We have 2 adjacent ones here. Well, our combined computation works on adjacent computation, so this is now amenable to combination, and it might be possible to send this in and of itself to a node. Now that seems kind of counterproductive. If we could just send both of these computations to a node to begin with, why bother sending this back to a node? Maybe this is something where I can practice a little bit with the tablet. So let me plug this in real quick. Let's see if I can find the plugin. This might be a disaster, but we'll try it. So, let's see, where is it? Is it detecting? Oh, okay, there we go. Okay, so the idea is that we had a main computation which was broken up into lots of different work units and so on. I'm doing a binary tree here, but it doesn't matter. And then each of these had, down more and so on. Let's use the example here that these are our main work units. Work units. That was really bad. Like I said, my handwriting isn't good. Units. So let's use, let me bring this over here. Let's use red as one of the nodes. So initially when we distribute the work, this is going to be computed by slave number one. This one was computed by number 2. This was computed by number 2. This was computed by number 1. That's one possibility of how the work was distributed. I mean, when number 1 was allocated work, then we can allocate number 2 immediately to the second thing. But maybe number 2 finished before number 1 finished right here. So this finished. So we can allocate number 2 to this next node to work in. But now number 1 finished, so we can allocate it to this. So one thing that we might ask is, so when we look at our bit vector, again, it starts off as 0, 0, 0, and 0. When our first one finishes, it's 1, 0, 0, 0. Our second one finished, 1, 1. Actually, let me erase this. I made a mistake. I said that the second one finished first. So this was 0, 1, 0, 0. But then we had 1, 1, 0, 0. And then presumably one of these will finish, so that'll be 1, 1. Let's assume that this one finishes. And then finally we have 1, 1, 1, 1. And we need to combine these. In the time that this guy finished right here, if it writes, oh, he's pressing a button. In the time that this finished right here, there's no more work that is available for that to do. Let me go to, I don't know, green. This one right here is already allocated number 1. So node number 1 is working on this one already. So node number 2, which this is what this one was working on, is free to go about anywhere. The next work that we need to do is combine different operations. Well, our master node might say, hey, there's still work to do. Let's combine these two guys, which is equivalent to computing this right here. So we'll actually assign this combination to number 2. While that's computing, number 1 will probably finish, and we can allocate this guy right here to number 1. Finally, when both of those finish, then we get the final computation. This one is kind of the final right here. This guy is going to be computed by the master node. So after this gets computed, we're going to get some ratio, mathematically speaking. This is going to lead to, let me kind of draw a little arrow. This is going to lead to some ratio P over Q. With pi, for example, we're going to need to transform this. We're going to need to transform this to something like the square root of, what is it, 640,320 or something, to the power of 3. And we need to multiply that by Q over P. So this thing, this node right here, only does this single, it computes the numerator and denominator, but there's still operations we need to do. We need to do this division, we need to do this trivial